Vom Verbrenner weg zur E-Maschine ist eine ziemliche Herausforderung.
Es gibt Millionen Art und Weisen, wie man elektrische Antriebe bauen kann.
For decades, engineers tried to put motors inside car wheels, but an invisible problem kept stopping them. Now, a new dual rotor technology claims to have cracked the code. Two rotors spin around a single stator, creating more power, insane efficiency, and almost unbelievable lightness. Could this mean cars will never need traditional drivetrains again? Could one wheel hold more power than an entire sports car? The possibilities are staggering, and the secrets inside these spinning motors could surprise the industry. Join us as we uncover how this breakthrough might reinvent the wheel forever. The power that never reached the road. Every electric car promises clean power and high efficiency. The motor is often praised as almost perfect, but there is a quiet problem hiding beneath the smooth body panels. A large part of the energy never reaches the road. It disappears along the way. In most electric vehicles, about 25% of the energy made by the motor is lost before it ever turns the wheels. This loss does not come from one single place. It comes from a long chain of parts that must all work together. Each part steals a little power. By the time the energy reaches the tires, a big portion is already gone. The motor usually sits in the middle of the car. From there, power must travel through a gearbox that changes speed and torque. Gears slide, press, and rotate against each other. Even with good oil and precise machining, friction is always present. After the gearbox, power moves into the differential. This part splits torque between the wheels, but it also creates heat and resistance. Then come the drive shafts, which spin at high speed and twist under load. Finally, constant velocity joints allow the wheels to turn and move with the suspension. These joints are complex and full of moving parts. Every bend and rotation eats away more energy. Each loss may seem small on its own. Together, they become a flood. The motor can be very efficient on a test bench, yet the car still wastes a large share of energy before motion even begins. Electric vehicles suffer more from this problem than combustion cars. This may sound surprising, but there is a clear reason. Electric motors deliver high torque instantly and at low speed. That strong twist must travel through every mechanical part from the first moment the car moves. Combustion engines build torque more slowly and often operate at higher speeds, where some drivetrain losses behave differently. Electric power is clean and immediate, but that also means the drivetrain feels every bit of force all the time. This problem is not new. Engineers noticed it more than a century ago. In the year 1900, Ferdinand Porsche built a car with motors placed directly in the wheels. It appeared at the Paris World Exhibition and worked very well. There was no gearbox, no drive shaft, no differential. Power went straight to the road. The idea was elegant and simple, but history took another path. Combustion engines improved quickly. Fuel became cheap and easy to store. Batteries, on the other hand, stayed heavy, weak, and expensive for many decades. Early electric cars could not travel far, and the extra weight of motors in the wheels made little sense at the time. The world chose gasoline, and the direct drive idea faded into the background. Still, the dream never fully died. Every few years, someone brought it back. Engineers showed drawings and test cars with motors in the wheels. The promise was always the same. Remove the drivetrain, remove the losses, make the car simpler and more efficient. And every time, the idea failed again. One reason was weight, but another was misunderstanding efficiency. Many companies focused on peak motor efficiency. They showed charts proving their motors were very efficient at full power. But real driving rarely happens at full power. Most driving happens at partial load. City streets, traffic lights, gentle cruising, and small speed changes dominate daily use. At partial load, losses behave differently. Rotational inertia becomes important. Heavy rotating parts resist changes in speed. Every time the driver accelerates or slows down, energy is wasted just spinning parts up and down. Friction losses also grow in importance at lower loads, where they make up a larger share of total energy use. A motor that looks amazing at peak output can still waste energy in normal driving. This is where marketing and reality part ways. Car makers often advertise motor efficiency numbers taken under ideal conditions. These numbers are real, but they are incomplete. What truly matters is how much energy reaches the wheels during everyday driving. That is wheel-delivered efficiency, and it is rarely shown in glossy brochures. Traditional designs accept these losses as unavoidable. The industry learned to live with them. Bigger batteries were added to hide the problem. Longer ranges were promised without asking where the energy was truly going. Yet, the truth remains simple. Energy that never reaches the road is energy that never moves the car. It becomes heat, it shortens the range, it increases costs, and it forces larger batteries, which add more weight and more expense. The power loss problem has always been visible, but it was easier to ignore than to solve. Fixing it would require rethinking the very layout of a car. It would mean questioning a century of design habits. That kind of change is uncomfortable, slow, and risky. Engineers knew the solution for over a century, so why did it keep failing every time? The unsprung mass wall that stopped everyone. The idea seemed perfect. Place the motor inside the wheel and send power straight to the road. No long shafts, no gears fighting each other, no wasted energy. Yet every time engineers tried, the same invisible wall appeared. That wall was an unsprung mass. Unsprung mass is the weight of everything below the suspension. This includes the wheel, tire, brake parts, and all components that move with the road. The suspension is designed to control this weight. It pushes the wheel down to stay in contact with the ground and pulls it back when the road drops. Lighter unsprung mass makes the suspension's job easier. The body of the car, the battery, and passengers sit above the suspension. This weight is called sprung mass. Springs and dampers protect the heavier part of the car from road shocks. The balance between sprung and unsprung mass is critical. When unsprung mass becomes too heavy, the suspension loses control. Adding a motor to the wheel changes everything. A motor is not light. Inside the wheel, all that weight becomes unsprung. The wheel is no longer just rolling. It carries a powerful spinning machine. Every bump now has to move not just rubber and metal, but a heavy motor. When the car hits a bump, the wheel wants to jump upward. The suspension tries to push it back down. With too much unsprung mass, it reacts too slowly. The wheel can leave the road for a moment. That moment is enough to lose grip. Steering feels vague. Braking becomes uneven. The car no longer feels planted. Ride quality suffers. Small bumps feel sharp. Larger bumps feel violent. Instead of absorbing the road, the car takes the impact directly. Passengers feel it immediately. Drivers sense it through the steering wheel and seat. Safety is affected because tires only work when they touch the road. If the wheel bounces, grip disappears. During braking, stopping distance increases. In corners, sudden loss of control can occur. No clever tuning can fully hide this. Engineers describe the problem simply. Driving with heavy wheel motors is like running while wearing cement boots. Every step feels slow and awkward. Balance suffers. This is why wheel motors kept failing. Even powerful, efficient motors made the car unpleasant to drive. Test tracks revealed the truth quickly. Cars felt harsh, nervous, and unpredictable. Professional test drivers noticed it immediately. They are trained to feel small changes. After a few laps, they knew something was wrong. Even small increases in unsprung weight have big effects. The suspension must control fast movements, not slow ones. Road impacts happen in fractions of a second. Dampers cannot react instantly to heavy objects moving quickly. Some thought software could fix it. Sensors and smart damping were suggested. But software cannot change physics. It cannot make a heavy object lighter. Mechanical inertia always wins. Springs and dampers can only do so much. Placement also matters. Heavy front motors are worse than rear motors. Front wheels steer, brake, and feel most of the road. Loss of grip there is noticeable. Rear wheels do not steer and often handle less braking. They tolerate slightly more weight without ruining driving feel. That is why many engineers revisited wheel motors for the rear axle first. The wall of unsprung mass is invisible but real. It cannot be bypassed. It must be understood, respected, and solved physically, not digitally. Until then, the perfect in-wheel motor remained out of reach. Then a group of young engineers decided the problem wasn't unsprung mass, it was motor design itself. Inside the dual rotor breakthrough. The breakthrough did not begin inside a factory or a boardroom. It began with young engineers who were still learning, questioning, and pushing limits. At the Technical University Munich Formula student team, students worked closely with electric race cars. They tested motors, measured efficiency, and watched where energy disappeared. Over time, frustration grew. The electric drive systems they studied were powerful, but they were also wasteful. Too much energy turned into heat instead of motion. After graduation, several of these engineers joined large companies. There, the frustration became even stronger. Production electric vehicles used systems that looked advanced on the outside but felt outdated underneath. Energy losses were accepted as normal. Improvements came in small steps. 5% here, 3% there. To these engineers, that was not enough. In 2021, they made a bold decision. They left their jobs and founded Deep Drive. Their goal was not to slightly improve existing motors. They wanted to rethink the motor itself. They chose to abandon incremental gains and search for a design that changed the rules entirely. The heart of their idea was simple but dangerous. Instead of using one rotor, why not use two? For over a century, electric motors followed the same pattern. A stator created a magnetic field. A single rotor moved inside or outside it. Deep Drive broke that pattern. Their design placed the stator in the middle. One rotor spins on the inside. Another rotor spins on the outside. Both rotors turn at the same time, perfectly synchronized. This creates a sandwich layout, with the stator trapped between two moving magnetic forces. This layout changes how magnetic energy is used. In a normal motor, magnetic interaction happens on one main surface. In the dual rotor design, interaction happens on two surfaces at once. The inner rotor and outer rotor both pull and push against the stator. This greatly increases the active magnetic surface without increasing the size of the motor. A more magnetic surface means more torque. Torque is the twisting force that moves a car. Because both rotors work together, their magnetic fields reinforce each other. This process is called flux reinforcement. Instead of fighting or canceling out, the magnetic fields overlap and grow stronger. The result is more force from the same space. This is why the torque numbers are so striking. Each in-wheel unit produces 2,000 Newton-meters of torque. That equals 1,475 pound-feet at a single wheel. This is not total vehicle torque. This is per wheel. Power output matches this strength. Each motor reaches 180 kilowatts of peak power. All of this fits inside a 19-inch wheel. That packaging alone sets it apart. High-torque motors usually grow large and heavy. This one stays compact. Torque density explains why. Torque density means how much torque a motor produces compared to its size and weight. The dual rotor layout allows torque density to scale upward without increasing diameter. Instead of making the motor thicker or wider, Deep Drive made it smarter inside. Another hidden advantage comes from balance. High-torque motors often suffer from axial force imbalance. This happens when magnetic forces pull unevenly along the axis of rotation. Over time, this creates wear, noise, and stress on bearings. The dual rotor design naturally reduces this problem. Forces from the inner rotor and outer rotor oppose each other in a balanced way. Pull from one side is matched by pull from the other. The stator stays centered. Stress is shared. This improves durability and smooth operation. The numbers also reveal what happens when multiple motors are used together. A vehicle with 4 of these motors could reach extreme total power and torque. Acceleration would be limited not by the motors, but by the tires. Rubber can only grip the road so much. Once grip is reached, adding more torque no longer helps. This is a key shift. In most cars, the drivetrain limits performance. Here, the road becomes the limit. Tire grip, not motor output, defines how fast the car can launch or turn. This matters for control as much as speed. With independent motors at each wheel, torque can be managed precisely. Each wheel can receive exactly the force it needs. Stability improves. Traction improves. Response becomes instant. The beauty of the dual rotor breakthrough is not just raw power. It is how efficiently that power is created. Instead of pushing harder with more material, the design uses physics more wisely. Magnetic fields are guided and reused. Space is used fully. Balance is built into the structure. But breaking one rule forced them to break another, the iron yoke itself. The yokeless motor and the copper architecture. For more than 100 years, electric motors followed the same hidden rule. Inside almost every motor sat a heavy ring of iron called a yoke. Its job was to guide magnetic fields and add strength. It did not create motion, yet it added weight. In electric vehicles, weight always reduces efficiency. In traditional motors, the yoke closes the magnetic path and keeps parts from bending under force. This comes with a penalty. The iron adds mass without adding torque. In a dual rotor motor, the yoke creates another problem. It increases the distance between the 2 rotors, which weakens magnetic interaction. Strong magnets lose effectiveness when separated by unnecessary material. Deep Drive removed the yoke completely. This decision changed everything, but also created new challenges. Without iron, the magnetic field still had to close properly. The motor still needed strength to resist powerful forces. Heat from the windings still needed a fast escape path. The magnetic problem solved itself through design. With magnets on both rotors, magnetic loops close directly between them through the air gap. North and south poles face each other and complete the path naturally. Iron is no longer required to guide the field. Structure was the next challenge. Magnetic forces pull hard from both sides. Without support, the stator could twist or vibrate. Traditional motors depend on iron for rigidity. Deep Drive replaced that function with copper. Most motors use copper wire windings. Wire is flexible and easy to install, but it can move slightly under force. Movement creates vibration and noise. It also limits heat flow because contact with the housing is small. Deep Drive uses copper bars instead. These solid bars form a truss-like structure. A truss gains strength from shape rather than mass. The bars lock together in geometric patterns that resist twisting. Each bar is anchored directly to the motor housing, giving the motor strength without iron. The copper bars also solve the heat problem. Copper moves heat extremely well. Heat flows straight from the windings through the bars into the housing. Coolant then carries it away. The structure itself becomes the cooling path. Removing iron brings another benefit. Iron changes shape slightly when magnetic fields pass through it. This effect creates vibration and sound. With most iron removed, this effect nearly disappears. The motor becomes smoother and quieter. Material savings are large. The design uses 80% less iron than traditional motors. Less iron means less weight and lower losses. Iron losses happen when magnetic fields cycle through steel and turn energy into heat. With less iron, these losses drop sharply. Efficiency improves most during normal driving. Cars spend most of their time at partial load, not full power. The Yokeless design wastes less energy in these conditions. This creates a 20% improvement in real-world efficiency. That efficiency turns into range. More energy reaches the wheels instead of becoming heat. A vehicle can travel farther using the same battery, or it can use a smaller battery to reach the same distance. Manufacturing also improves. Copper bars can be cut and placed with robotic precision. There is no hand winding. There are fewer steps and fewer errors. This lowers cost and improves consistency. By removing the yoke, Deep Drive did not weaken the motor. They replaced iron with geometry, copper, and smart design. Structure, cooling, efficiency, and cost improved together. The copper architecture became the backbone of the motor, holding everything in place while letting energy flow freely. Compared with wire windings, copper bars stay fixed under load. They do not shift when magnetic forces rise. This stability protects efficiency over time. Compared with hairpin windings, the bar design remains simpler and stronger. Hairpin system freedoms still rely on layered steel cores. The copper bar system replaces several parts at once. Fewer parts mean lower cost and easier scaling. Because the same structure carries force, heat, and current, the motor becomes easier to build in large numbers without special factories. This balance allows the design to grow from prototype to mass production, while keeping performance stable, cost predictable, and efficiency high across every driving condition. Even the best motor fails if it destroys ride quality, unless the entire corner is redesigned. Solving unsprung mass by removing what was already there. For decades, engineers believed adding power to the wheel would always add weight. That belief stopped progress. Chapter 5 reveals how the problem was solved not by adding parts, but by removing parts that already existed. This change reshaped braking, comfort, and vehicle design. The breakthrough came through a partnership with Continental. Instead of treating the motor and the brake as separate systems, they were merged into one integrated drive-brake unit. This single unit replaces the traditional brake assembly found in most vehicles. Calipers, discs, hydraulics, and many supporting parts are no longer needed. Traditional brakes add heavy, unsprung mass to the wheel. They sit outside the suspension and move with every bump. When engineers tried to add in wheel motors on top of these systems, the weight became unacceptable. Ride quality suffered. Safety margins dropped. Drivers felt harshness and noise. By integrating braking into the motor, that extra weight disappears. The brake no longer sits beside the wheel system. It becomes part of it. Because the old brake hardware is removed, the motor does not add mass on top of existing parts. It replaces them. The result is a near-neutral, unsprung mass outcome. This solution only works because modern electric vehicles rely heavily on regenerative braking. During normal driving, the motor slows the car by turning motion back into electricity. Mechanical braking is used far less often, mostly for emergencies or very low speeds. This allowed engineers to rethink braking completely. The new system uses dry braking. There are no hydraulic lines, no brake fluid, and no pressure pumps. Removing hydraulics reduces weight and complexity. It also improves reliability. Fewer moving parts mean fewer failure points. Emergency braking is handled through smart logic. When maximum stopping power is needed, the system blends regenerative braking with the integrated mechanical brake. This brake engages instantly and directly. Because it is built into the motor structure, response is fast and controlled. The rear axle strategy plays a key role. Most braking force during normal driving already comes from regeneration at the rear in electric vehicles. By focusing integration there, engineers gained the biggest benefit with the least compromise. This also improves stability and control. Noise, vibration, and harshness matter deeply to luxury brands. Silence is not a bonus. It is a requirement. Traditional brakes create dust, squeal, and vibration. Hydraulic systems pulse and transmit noise through the chassis. The integrated system removes many of these sources. Magnetostriction noise is eliminated because the motor uses far less iron. The rigid copper bar structure prevents vibration from forming. Copper bars are anchored firmly and do not flex. This stability stops sound before it begins. The result is near-silent operation, even under load. This silence changes how cars feel inside. With no brake noise and no motor whine, cabins become calmer. Designers can focus on comfort instead of masking sounds. This is especially important for premium vehicles where quietness defines quality. The architecture is plug and play. Automakers can choose a central drive version or an in-wheel version using the same core technology. This flexibility lowers development cost and shortens timelines. One system can serve many platforms. Interior packaging also improves. Removing bulky brake systems and reducing drivetrain parts frees space. Floors can be flatter. Cabins can stretch forward. Designers gain freedom they never had before. New vehicle shapes become possible. This opens the door to new vehicle architecture. Cars no longer need to be built around old mechanical limits. Weight moves lower. Space moves inward. Balance improves naturally. Development follows a clear path. Small-scale production is planned by 2026. Mass production is targeted for 2028. This gives automakers time to adapt platforms while keeping risk low. Why BMW's validation changes the industry's risk model. BMW rarely moves first, and that caution defines its power. The company studies, waits, and only acts when risk becomes measurable. That behavior is why its involvement matters so deeply. When BMW touches a new technology, the industry pays attention. This chapter is not about motors or copper. It is about trust, risk, and what changes when a careful giant steps forward. BMW uses a venture client model, not a supplier bet. Instead of buying equity or making promises, BMW buys results. Startups must prove performance inside real BMW systems. There is no protection, no shortcuts, and no marketing shield. If the technology fails, it ends quietly. This model removes hype and replaces it with evidence, which lowers emotional risk while raising technical standards. Installing experimental motors into road-going test vehicles is not symbolic. It is costly and serious. These vehicles must meet internal safety rules, control standards, and durability expectations. BMW does not test ideas on paper for long. Real vehicles mean real consequences. This step signals confidence that the system is not fragile, unstable, or unsafe under daily driving conditions. BMW testing is known for overstress validation. Components are pushed beyond expected limits. Heat cycles repeat far past normal use. Cold starts follow extreme loads. Endurance runs continue long after typical failure points. Startups rarely overperform this early. Most struggle just to survive baseline tests. Passing advanced validation, this soon suggests the system behaves predictably under harm. Thermal cycling is especially unforgiving. Materials expand and contract. Connections loosen. Cooling paths reveal weakness. BMW tracks efficiency drop, noise change, and structural drift over time. Surviving these cycles shows the design is not just clever, but stable. Stability reduces risk more than raw performance, because car companies fear failure more than lost speed. Continental's parallel involvement changes the picture further. Continental understands braking systems, safety rules, and global certification paths. Their presence lowers supply chain uncertainty. It also accelerates homologation because regulators already trust Continental processes. When both BMW and Continental move in parallel, risk collapses from multiple directions at once. This combination changes timelines. Automakers normally wait years after a breakthrough before adoption. Validation, sourcing, and certification slow everything down. Here, those steps begin early. Testing happens while design matures. Manufacturing plans grow alongside validation data. This overlap compresses time and reduces surprises, which executives value more than bold promises. Even if the motors work, can the materials world keep up? The material equation that could decide everything. Electric vehicles are often defined by their batteries, but the hidden story lies in the materials that make their motors spin. Rare earth magnets, not lithium cells, are emerging as a critical bottleneck in global EV production. Most modern electric motors rely on neodymium, dysprosium, and other rare earth elements to generate the strong magnetic fields needed for torque. These elements are expensive, environmentally taxing to mine, and concentrated in a handful of countries. Any disruption in supply can delay production lines, spike costs, and create geopolitical tension, making magnet efficiency as crucial as battery chemistry itself. Traditional motors use thick magnets to produce high torque, which means heavy reliance on rare earths. Increasing torque usually requires adding more magnet material, directly increasing cost and exposure to supply chain risk. Dual rotor technology changes this equation. By placing rotors on both sides of the stator, the magnetic flux from each rotor reinforces the other. This overlapping of magnetic fields allows the motor to produce the same or higher torque with thinner magnets. Magnet thickness can be cut by up to 50% while maintaining peak performance. That reduction is not just technical, it is strategic. Less rare earth usage reduces supply chain vulnerability, lowers material cost, and makes production less sensitive to geopolitical shocks. Iron is another material under scrutiny. Most conventional motors use significant amounts of electrical steel in stator cores and rotor backs to guide magnetic fields. This steel is cheap and abundant, but requires energy-intensive processing, including mining, smelting, and lamination. Each kilogram contributes to production cost, carbon emissions, and energy consumption. Dual-rotor yokeless motors eliminate most of this steel. Removing up to 80% of the iron cut's weight reduces losses and lowers production energy requirements. Reducing material intensity has ripple effects across the EV lifecycle. A motor that requires fewer rare earths and less steel is lighter, which increases vehicle efficiency. A lighter vehicle needs smaller batteries for the same range, reducing material extraction, production energy, and overall emissions. Manufacturing time shortens because simpler motor designs are easier to assemble at scale. Less reliance on laminated steel cores means fewer steps, fewer machines, and less room for error, accelerating production ramp-up. From an industrial perspective, these material efficiencies directly influence cost competitiveness. EV makers are under pressure to deliver affordable vehicles without compromising performance. Motor materials now define a large portion of that balance. Reducing magnet and iron consumption lowers the per-unit cost of torque dramatically. For automakers, this can be the difference between profitable mass-market adoption and niche, high-cost offerings. Geopolitics also plays a role. Rare earth production is heavily concentrated in select regions, and supply chains remain vulnerable to trade restrictions, price fluctuations, and extraction bottlenecks. Cutting magnet demand in half through dual-rotor design reduces exposure to these risks. It creates flexibility for sourcing, long-term contracts, and even recycling programs, making the EV industry more resilient to external shocks. The environmental benefits are equally compelling. Fewer raw materials mean less mining, less energy use, and lower greenhouse gas emissions. Steel production alone accounts for significant carbon output globally. Reducing reliance on it in motor design translates into lower life cycle emissions for each vehicle. When multiplied across thousands or millions of vehicles, the impact becomes substantial, helping automakers meet both regulatory standards and sustainability goals. If you enjoyed this video, like and subscribe, and also click the next video shown on your screen.